The Saturn V launch vehicle, this is the largest and most powerful rocket ever flown. It carried astronauts to the moon in July 1969. How did we get there? The new president, John F. Kennedy, proclaims early in his administration that the United States will get astronauts to the moon by the end of the decade. Now, you have to keep in mind at this time, this is the height of the Cold War between the United States and the Soviet Union. The Soviets had launched Sputnik, the world's first artificial satellite, in October 1957. They were the first to put a human into orbit in 1961, and the United States was behind. This was a lofty goal to try to make America's stamp on the world. We were going to get humans to the moon. This posed a major technological challenge for the new space agency, the National Aeronautics and Space Administration. Now, at the time, the military departments, the Air Force, the Navy, and the Army had ballistic missiles, long-range ballistic missiles. NASA took advantage of ballistic missile technology for civilian spaceflight. So in 1961, NASA puts Alan Shepard on the top of an Army Redstone missile for America's first suborbital flight. Does the same thing with the Titan launch vehicle. To get humans to the moon, that's a big jump because you're going much further, and that requires a major leap forward in technology. That's how you get the Saturn V. The Saturn V at 363 feet is a three-stage rocket. It's going to be the most powerful one ever flown. How do you get there? Well, the key is scaling up that technology, but NASA had to consider a number of trade-offs. So they have to some extent, push the technological frontier to get there in terms of thrust and power of the engines, but they also have to weigh, at the same time, the safety of the crew. So there's safety and reliability and pushing the technological state of the art. And that's kind of there's a key tension there that has to be taken into account. So I mentioned earlier the Redstone ballistic missile that NASA used to send Alan Shepard into suborbital flight. You think about the thrust of that, 75,000 pounds of thrust in that engine. You go up to the Saturn V, the F1 engine, which powered the first stage of the Saturn V, 1.5 million pounds of thrust. That's a huge jump in thrust. How do you get there? So what NASA engineers have to do is they have to develop materials that are strong enough to withstand the enormous pressures and strains on the engine itself. A rocket engine is a controlled explosion, essentially. So the NASA engineers have to develop materials that are strong enough to do that. So it's a combination of science, it's a combination of some engineering, and of some craft knowledge. So those are some of the trade-offs that NASA engineers had to think about when they were developing the Saturn V. The rocket itself performed flawlessly in 1969, all the way up until 1972 with the last lunar mission. And something to keep in mind, I think, that is very important is that chemical propulsion of the type that was used in the Saturn V F1 engine and in all the liquid fuel rocket engines prior to that and all the liquid fuel rocket engines since then, that's the mainstay of our space launch vehicle capability in the United States. It hasn't changed, primarily because there's no alternative that has come along that's more efficient, more cost-effective, safer. So what NASA engineers are doing is they're trying to squeeze more efficiency out of a technology that has existed for decades.
It's time for rocket science. Rockets offer a fundamentally different approach to propulsion. Rockets do not beat the air into submission and do not depend in any way on aerodynamic forces to generate lift. Rockets also do not have to rely on the atmosphere for combustion, which is at the heart of all jet engines and all internal combustion engines. However, rockets must still pass through the atmosphere on their way to space, and in so doing, the rocket flight must remain stable. Early rockets, such as the German V2, were stabilized by a set of 4 fins. The function of the fins is to provide some surface area for aerodynamic forces to act upon, which shifts the center of pressure further back along the rocket. For stable flight, the center of pressure where the net aerodynamic force acts, must be aft of the center of gravity. So when a disturbance of some kind perturbs the rocket to some angle of attack relative to its flight path, the net force produced by the rocket body at an angle is acting aft of the center of gravity, creating a restoring moment that realigns the nose with the flight path. This is exactly the same idea behind the tail on an aircraft. Now, the fins have to be properly sized in order to work. Let's take a look at two rockets, one with adequate fins, the other with fins that are too small. I've tied a piece of string at the center of gravity of each rocket and will spin them around to induce airflow. Let's take a look. When I spin around the rocket with larger fins, we see that the rocket maintains stable flight, with the nose pointed in the right direction. Even when I give it a perturbation, it still keeps going in the right direction. So the fins are working as they should. But let's take a look at the rocket with small fins. On this rocket, the fins are probably too small, so I have some concern about whether this rocket is stable. Before we launch such a rocket, it's best that we test it before an actual launch where it might go unstable. So let's try this one out. And look, it just never gets going in the right direction of flight. No matter what I do, even with the perturbations, it still is in an unstable direction because the fins are too small and the center of pressure is ahead of the center of gravity. So any perturbation causes the angle of the rocket body with respect to the flow, causes the net aerodynamic force to act ahead of the center of gravity, which causes the rocket to tumble. So this condition is inherently unstable and would be extremely hazardous to the rocket and to people on the ground. Now, modern rockets don't have fins, or if they do, they're very small, like those on the Saturn V. How do these rockets remain stable? Well, the rocket engines are actually gimbaled, meaning that the thrust from the rocket engines is vectored as needed to maintain stable flight. Most modern rockets use gimbals instead of fins in order to reduce the weight and aerodynamic drag of the launch vehicle. So let's now focus on how a rocket engine works. Like a jet, the main force present in rockets is thrust, and that thrust is achieved by producing high pressure inside the combustion chamber and nozzle relative to the ambient pressure. The pressure difference creates a force that pushes the rocket along, and as a result of the pressure difference is an acceleration of propellants. But unlike a jet, rocket engines can easily operate outside the Earth's atmosphere, where there is absolutely no oxygen available for the combustion process. This is because rockets carry along their own oxidizer needed for combustion of fuel. In fact, the presence of the atmosphere is mainly a limiting factor for rockets. It drives some of the structural design requirements. The dynamic pressure, proportional to the density and square velocity, directly influences the aerodynamic loading on the rocket body. If you've ever watched a space shuttle launch live, you've heard the narrator call out max Q, which is the point in the flight where the maximum dynamic pressure occurs. Why is there a maximum? Well, the rocket is accelerating, so the velocity continues to increase throughout the ascent. But on the other hand, the density is decreasing as the rocket ascends out of the atmosphere. So this increase in velocity and decrease in density during the ascent will result in a maximum dynamic pressure at a certain altitude. Since it's a strong driver of structural loading, the engineers monitoring the flight take note of when the point of maximum dynamic pressure has occurred. Beyond the huge advantage of atmospheric independence of rockets, another significant advantage is that they produce a huge amount of thrust. For this reason alone, rockets have seen some limited use on aircraft, including the Bell X-1, which was the first aircraft to fly faster than the speed of sound. But because the rocket engine must carry the fuel and oxidizer, the weight and efficiency of the system is poor. So rockets are not very popular for use on aircraft. Since rockets are currently the only viable propulsion system for getting a payload into space, let's spend a little time considering rocket propulsion and how to get into orbit. Let's start with finding the thrust produced by a rocket, which is due to the pressure inside the combustion chamber being much higher than ambient, and this pressure difference accelerates the propellants. The dominant factors that describe thrust production are the mass flow rate of the propellant expelled from the nozzle and the exit velocity of those propellants. A rocket plume with high mass flow and high exit velocity will generate the highest thrust. It turns out that the same thrust equation that we used for the jet engine is applicable here, which is an expression of Newton's second law. But we're going to modify the equation in a couple of ways. First, there is no flow of air through the rocket engine, so the free stream velocity term drops out. Next, the combined mass flow of air and fuel can be simply expressed as the mass flow rate of propellant products out of the rocket nozzle. And finally, we need to add a term that describes the pressure difference between the flow at the exit plane and the ambient atmosphere. As long as the exit pressure of the nozzle is greater than the surrounding atmospheric pressure, this pressure difference will act on the area of the rocket nozzle and add to the overall thrust. Of course, as the rocket ascends through the atmosphere and the ambient pressure drops, the magnitude of thrust from this pressure difference will go up. So let's consider how we can optimize rocket performance. We'll start by defining the specific impulse of a rocket, which is a measure of how efficiently the rocket produces thrust. Impulse is the magnitude of a force applied over a certain period of time. High impulse can be achieved by producing a large force within a short period of time, such as a bat striking a baseball. Or high impulse can be achieved by a relatively low force applied continuously over a long period of time, such as pushing a box to slide it down a long corridor. Specific impulse is the same idea, except that the adjective specific indicates that the impulse is normalized by weight. So specific impulse for a rocket is found by the thrust of the rocket divided by the time rate of change of weight. Or we could also express specific impulse as thrust divided by the product of mass flow rate and standard gravitational acceleration at Earth's surface. Note that the use of gravitational acceleration is an agreed upon convention, with a value of 9.81 meters per second squared or 32.2 feet per second squared is always used in the calculation of specific impulse, no matter where the rocket is within the universe. Specific impulse, then, has units of pound-seconds per pound, or simply seconds. We can think of it as the force applied over a given length of time divided by the weight. Or we can think of it in this way. For each pound of combustion products, for what duration of time can the rocket produce a pound of thrust? Now, let's take specific impulse and combine it with our equation for thrust, which equates thrust production to the mass flow rate times the exit velocity. When we merge these two ideas, we see that the mass flow rate cancels out in the numerator and denominator, and we're just left with the specific impulse being equal to exit velocity divided by the gravitational acceleration constant. So to optimize the efficiency of a rocket, we need to maximize the exit velocity. In order to get the exit velocity of the propellant as high as possible, the stagnation temperature in the combustion chamber must be as high as possible. The main connection here is that temperature is a measure of the internal energy of the combustion products, and that energy must be conserved. The rocket nozzle serves to thermodynamically expand the combustion products from essentially zero velocity up to incredibly high exit velocity by exchanging the thermal energy of the combustion products into kinetic energy of the exiting flow. By conservation of energy, if we assume an adiabatic situation where there is no heat loss through the walls of the rocket nozzle, there must be a direct balance between this internal energy and the kinetic energy. An expression for the conservation of energy, written out for a rocket nozzle, shows that the exit velocity is proportional to the square root of the ratio of stagnation temperature to the molecular weight of the combustion products. That is, high-efficiency rocket engines should have high combustion temperature but lightweight propellants. Now, how can we get high-temperature combustion products with low molecular weight? Both of these parameters depend on the particular rocket propellant and oxidizer used for the combustion process. There are two main types of rocket propellant systems, solid and liquid. Solid propellant systems have the fuel and oxidizer pre-mixed and cast into a solid form. This is what was used on the Space Shuttle's twin solid rocket boosters, or SRBs. There, the propellant consisted of atomized aluminum powder as a fuel and ammonium perchlorate as an oxidizer, with a small amount of iron oxide powder as a catalyst. This fuel oxidizer catalyst combination is then mixed with a rubber-based binder to hold everything together. The advantages of solid propellant are that it avoids the complexity of large pressurized storage tanks for fuel and oxidizer, it is less volatile, and more reliable. However, once a solid rocket is lit, there is no way to shut it down, and little that can be done to throttle it. And another disadvantage is that the best specific impulse available from solid propellant is in the range of 200 to 300 seconds, and is typically less than what could be attained from liquid propulsion concepts. Now, an interesting feature of solid propulsion is the thrust profile produced by the burn. The thrust is proportional to the exposed surface area that is being actively burned. An end-burning configuration will produce relatively constant thrust throughout the burn, since the surface area doesn't change. Another common configuration is one with an internal bore, where burning occurs along the entire surface of the internal bore. Under this configuration, the thrust will increase over time since the surface area is increasing. Or another configuration is an internal bore with a star configuration, where the surface area is a maximum at the outset and then gradually decreases as the points of the star burn. The shuttle's SRBs had an 11-point star, which produced maximum thrust at liftoff, followed by a reduction in thrust through the remainder of the burn. Let's talk through a test firing experiment with a model rocket engine that I have actually conducted. The engine for my rocket uses solid propellant with a small internal bore that partially penetrates the core of the propellant. The rocket has an initially high transient thrust due to the larger surface area of the propellant. This high initial thrust is designed to quickly accelerate the rocket for stable flight. But then the propellant transitions into an end-burning configuration, producing constant thrust for the remainder of the burn until exhaustion of propellant. Now let's turn our attention to liquid propellants. The main idea is to inject the propellants at very high pressure into a combustion chamber. One of the most common rocket fuel and oxidizer combinations is liquid hydrogen and liquid oxygen. The combination of these two produces a very energetic reaction that results in heat and water. The resulting specific impulse of this combination can be as high as 455 seconds for a vacuum. Since the propellants must be stored in liquid form in order to keep the volume down, the storage temperatures have to be below the vapor temperature of 20 Kelvin for hydrogen and 135 Kelvin for oxygen. The entire process of fueling and onboard storage must be done at these cryogenic temperatures. For delivering the fuel at high pressure for the combustion event, there are two main pressure systems. First is a pressure-fed system, where the fuel and oxidizer are stored at high pressure. A high-pressure inert gas is stored upstream of the liquid fuel and valved to supply the driving force to push the propellants into the combustion chamber. This system affords the advantage of simplicity, but the storage tanks are thick-walled and heavy in order to contain the high pressures involved. For this reason, pressure-fed systems are typically used only for small-scale rocket engines, such as thrusters for orbital maneuvering. The second method of delivering propellant at high pressure is to use fuel pumps. These boost the pressure of the propellants right before pumping them into the combustion chamber. Because pressure is lower until boosted, the fuel storage tanks can be constructed with considerably less mass. The fuel pumps are often staged to provide incremental boosts in pressure at reasonable efficiency levels. And the pumps are driven by various schemes, including pre-burning a small amount of fuel and using the exhaust gases to drive a turbine, which then mechanically drives the fuel pump. So whether the propellants are solid or liquid, when they undergo the combustion process, there will be a specific temperature at which they burn, the adiabatic flame temperature for the fuel oxidizer combination. And as we saw in our discussion of thrust and exit velocity, we need to maximize the stagnation temperature for optimal performance. This drives rocket scientists to select the hottest burning fuel combination possible, given the other design constraints. And given the stoichiometry of different combinations, the combination of liquid hydrogen and liquid fluorine is about optimal, giving an adiabatic flame temperature of 4,756 Kelvin and a specific impulse of 390 seconds. However, fluorine is corrosive and poisonous, making it extremely difficult to handle. So liquid hydrogen and liquid oxygen are often used instead, with almost the same level of performance. Now let's hone back in again on the thrust equation. We saw from the definition of specific impulse that we need to optimize the thrust. And from the thrust equation, we see that both the exit velocity and the mass flow rate must be maximized. Up to this point, we've been discussing ways to optimize the exit velocity, but let's focus on mass flow rate for a moment. The pressure in the combustion chamber of a rocket is so high relative to the ambient pressure at the exit that the flow through the rocket nozzle is supersonic. In our discussion of aerodynamics so far, we haven't yet discussed the nature of supersonic flow within a nozzle. It turns out that there are some interesting quirks that challenge our understanding of fluid flows. First, the concept of conservation of mass predicts some intriguing results for a supersonic flow. We know that for a subsonic flow, the cross-sectional area of a duct must decrease in order to accelerate the flow. However, for a supersonic flow, the situation is the exact opposite. In order to accelerate a supersonic flow, we must increase the cross-sectional area of a duct. This is because downstream information, such as any changes in geometry, cannot be communicated upstream for the flow to adjust accordingly. Increasing the duct area of a supersonic flow is required to allow the flow to expand, the density to go down, and the Mach number to continue to rise above sonic conditions. So the only way to accelerate an internal flow from rest up to supersonic speed is to pass the flow through a nozzle that is converging and then diverging. The point of the minimum area is the choke point, where the local velocity is sonic. So this fact is why rocket nozzles are bell-shaped with increasing area. The flow velocity is very close to zero within the combustion chamber, but is accelerated in a short distance to sonic conditions at a throat. Then downstream of the throat in a rocket engine, there is a large bell-shaped nozzle that further expands the flow to supersonic speeds. And since we want the exit velocity to be as high as possible, it's imperative that the exit velocity be supersonic. Now, if the flow is choked at the throat of the nozzle, which implies fixed mass flow rate through the system, what can be done to increase the mass flow rate of propellants through the rocket? Well, the mass flow rate can be increased in order to increase the thrust by increasing the stagnation pressure in the combustion chamber. The pressure provides the driving force to push more mass of propellant through the system. The pressures and mass flow rates for rocket engines can be amazingly high. For example, on the Space Shuttle main engines, the stagnation pressure in the combustion chamber was a whopping 210 times atmospheric pressure, and the mass flow rate of the propellants through the engines was on the order of 16,000 gallons per minute. Now, a key result for rocket scientists is the final velocity at the completion of a rocket burn. Let's think about the most critical parameters that would dictate the total amount of acceleration provided to the rocket. First, we know from Newton's second law that the acceleration results from an applied force, which is the rocket thrust in this case. And the thrust of the rocket is related to the mass flow rate of propellant and the velocity of the propellant exiting the exhaust nozzle. So clearly, if a rocket burns more mass of propellant, it will achieve a higher velocity increment. But for a given mass of propellant, it also matters how efficiently the energy of propellant mass is converted into thrust by expelling the mass from the nozzle with high kinetic energy. These factors can be encapsulated in the rocket equation, which expresses a velocity increment as the product of specific impulse, standard gravitational acceleration, and the natural logarithm of the ratio of initial mass to final mass. In the rocket equation, the log of the mass ratio represents how much propellant is burned, and the specific impulse represents the efficiency of the thrust production process. This is a highly useful equation, since it tells us how fast the rocket will be moving after burning a certain mass of propellant. Or if we solve for the mass ratio, the equation tells us how much propellant mass is required for a desired final velocity of a rocket. Now, when we take a look at rockets designed to carry people or payload into space, we see an interesting feature common to all of them. The Saturn V, Space Shuttle, Delta IV, Space Launch System, Ariane 5, and Falcon 9 all have multiple stages. A staged rocket is one that is segmented, with a separate rocket engine, nozzle, propellant storage, structure, and control system for each stage. The number of stages is typically 2 or 3, and sometimes 4. Now, why in this world, or why out of this world, would a rocket designer add that extra complexity to the vehicle design? Well, we have to start by considering how much propellant it takes to get a payload to orbit. It turns out that the typical payload fraction of the overall mass of the rocket is a mere 5%. The biggest driver of vehicle mass is propellant. This comes in at 80 to 85% of the overall rocket mass. This number is particularly stunning when we compare it to the already impressive fuel weight fraction of 50% that we saw for long-range commercial airliners. So if over 80% of a rocket is for propellant and 5% is for payload, the remaining 10 to 15% is for structure, propellant tanks, plumbing, and systems to support the payload and successfully operate the rocket. For a single-stage rocket, the mass fraction for the structure will scale with the mass of the propellant. And we saw a few minutes ago that the mass of propellant depends on the required velocity at the completion of the rocket burn. Now, if a single-stage rocket were used to put a payload into orbit, a massive amount of propellant is burned over time, leaving significant empty structure that must be designed into the vehicle in order to sustain the initial mass of the rocket. Once the propellant is burned, however, the structure needed to support that propellant is now dead weight. So the idea of staging is to drop that weight as the vehicle continues to climb. When a multi-stage rocket is designed, the latter stages are sized based on the lighter weight of the remaining vehicle. From an overall system standpoint, a thoughtfully designed multi-stage rocket requires less total propellant than a single-stage rocket designed to accelerate a given payload to the required velocity. We can see this through a side-by-side comparison of a single-stage rocket and a two-stage rocket, both with a total vehicle mass of 10,000 kilograms and designed to accelerate a payload to orbital speeds of 9.3 kilometers per second. Both vehicles employed the same rocket engine, whether one or two stages, with a specific impulse of 430 seconds. If we make an assumption that the rocket's structural mass is 10% of the total vehicle mass, then we can do some analysis. For the single-stage vehicle, the total mass of 10,000 kilograms requires a propellant mass of 8,900 kilograms, or 89% mass fraction, to accelerate the 100 kilogram payload to a final speed of 9.31 kilometers per second. This directly comes from our application of the rocket equation and solving for the required propellant mass to accomplish this goal with a single engine. Now let's consider the two-stage option. First, we'll constrain the entire vehicle mass to remain at 10,000 kilograms, the final speed to be 9.31 kilometers per second, and the specific impulse of each rocket engine at 430 seconds. We'll maintain a fixed ratio of 10% structural mass for the overall vehicle, and for the second stage at the beginning of its burn. We'll also assume that the mass of the second stage at the beginning of its burn is 30% of the total rocket mass, or 3,000 kilograms. Given these constraints, we can use the rocket equation to find the mass of propellant required for each stage and the resulting velocity at the end of the fuel burn for each stage. The result is a total propellant mass of 8,408 kilograms, compared to the propellant mass of 8,900 kilograms for the single-stage design. We've saved 492 kilograms of propellant mass. This savings in propellant mass can be added onto the payload weight, bringing it up from 100 kilograms for the single-stage design to 592 kilograms for the two-stage design. Now we're beginning to see the benefit of multi-stage rocket design. Now, what happens to the used stages that separate and fall away? The easiest approach is to simply jettison the lower stages and allow them to fall into the ocean as scrap, as done with the Saturn V. Or expended upper stages, which separate on the edge of space, get burned up by atmospheric heating as they re-enter Earth's atmosphere. In either case, the expended stages are thrown away, which is very expensive. Clearly, the launch provider would prefer to reuse the structure of the expended stages in order to achieve cost savings. One of the most common techniques is for the stage to descend via parachute. This is exactly what the Space Shuttle solid rocket boosters were designed to do. The solid rocket boosters would fire continuously for about the first 2 minutes of flight. Following shutdown of the boosters, they would separate from the large external fuel tank, and parachutes would deploy to carry them down for an oceanic landing. Ships then would recover the SRBs and tow them back to a refurbishment facility. However, the effects of salt water on the SRBs was harsh and corrosive, requiring extensive refurbishment before the SRBs could be reloaded with propellant and used again. Now, the ideal scenario, but also the toughest challenge, is to bring the rocket back down to its launch pad, landing straight up. This is the ideal situation since it would incur the lowest cost to refurbish the rocket, turning it around for a second flight. Landings of this type have included SpaceX with their Falcon 9 and Blue Origin with their New Shepard, both of which have successfully landed, refurbished, and reused a rocket. What makes it such a challenging problem is maintaining stable flight of the rocket as it comes back down. The orientation of the rocket is inherently unstable. In fact, the challenge is not unlike trying to balance a broomstick in the palm of your hand. It takes continuous and active feedback to balance the long, slender body of the rocket, since the center of gravity of the body is so high. But careful application of directed thrust with robust control schemes now makes it possible to stick this kind of landing. So in summary, the thrust of a rocket depends on the mass flow rate of the propellants through the nozzle and on the exit velocity of those propellants. In order to optimize the thrust and efficiency of a rocket engine, we need high temperature and pressure in the combustion chamber and a lightweight propellant. Both solid and liquid propellant rockets are widely used today in order to produce the high impulse needed to accelerate a rocket to high speeds. The velocity at the end of a given burn of rocket fuel is governed by the rocket equation, which depends on the specific impulse and the ratio of initial to final mass. We also saw how the rocket equation can be applied to a staged rocket, with multiple stages helping to reduce the amount of empty or wasted mass being transported once a certain amount of propellant has been burned. Now, based on this exit velocity, we'll see what type of orbit we can enter. It turns out that the final velocity at cutoff of the rocket engines is critical for determining whether the spacecraft will immediately come back down via a suborbital trajectory or whether it will stay in orbit around the Earth. So now you can legitimately say that you know something about rocket science.